Good day everyone! Welcome back to General Mathematics. It is still me, Engineer Omengan, to teach you logarithmic functions. Welcome to Logarithmic Functions, LBV GMath 1-5.4. In this topic, our most essential learning competency represents a logarithmic function through its A. Table of values, B. Graph, and C. Equation. The topics covered in this video are table of values of logarithmic functions, graph of logarithmic function, parts of logarithmic function, and characteristics and restrictions in logarithmic function. For our learning objectives, by the end of this video, we want to learn how to graph a logarithmic function, supply missing values in a table of values of logarithmic function, and determine the parts, trends, restrictions, and characteristics of a logarithmic function. Now let's discuss the representations of logarithmic function. Functions can be represented in three ways. First is by table of values, second is by graph, and third is by its equation. Let's try to solve this problem. Determine the outcome of the function f of x equals log of x to the base 2 given that x is equal to 0.25, 0.5, 1, 2, and 4. Now that we are given here the values of x and we are required the values of f of x or y, we will just substitute these x values to our function. For x equals 0.25, we will have log of 0.25 to the base 2 and that is negative 2. For x equals 0.5, we will have log of 0.5 to the base 2 and that is negative 1. Next, for x equals 1, we have log of 1 to the base 2 and that is 0. Next, for x equals 2, log of 2 to the base 2 and that is 1. And for x equals 4, we have log of 4 to the base 2 and that is equal to 2. Now that we have all these x and y values, we are now going to plot these points. From our functions, log of x to the base 2, we acquired the following points: 0.25, negative 2, 0.5, negative 1, 1, 0, 2, 1, 4, 2. Given these points, we will just plot these points in our graph and we will just connect them. So we have here 0.25, negative 2, 0.5, negative 1, that is this point, 1, 0 is this point, 2, 1 is this point, and 4, 2 is this point. We will just connect these points, and now we will have the graph of the function log of x to the base 2. Let's try another problem. Determine the outcome of the function f of x equals log of x to the base 3 given that x is equal to 0.11, 0.33, 1, 3, and 9. Again, since we are given here the following x values, to acquire the f of x, we will just substitute these x values to our function. For x equals 0.11, we have log of 0.11 to the base 3, and that is negative 2. Next, for x equals 0.33, we have log of 0.33 to the base 3, and that is negative 1. For x equals 1, we have log of 1 to the base 3, and that is 0. For x equals 3, we have log of 3 to the base 3, and that is positive 1. For x equals 9, we have log of 9 to the base 3, and that is positive 2. Now that we have the following x and y values, these points can be now plotted to our Cartesian plane. Again, for our function f of x equals log of x to the base 3, we acquired the following set of points. X equals 1/9, y equals -2, 1/3, -1, 1, 0, 3, 1, and 9, 2. Now that we have these points, we will now plot them. So we have 1/9 or 0.11, -2, 1/3 or 0.33, -1, 1, 0, 3, 1, and 9, negative or positive 2. Connecting these points will give us our graph of the function. For our last example, let's supply the missing values. Determine the outcome of the function f of x equals log of 2x minus 1. We can see here that the base is not indicated, so we can assume that it is a common logarithm or a logarithm with base 10, given that x is equal to 1, 1.25, 1.5, 1.75, and 2. Again, since we are given the x values, we will just substitute it to our function. So for x equals 1, we will have log of 2 times 1 minus 1, and that is 0. For x equals 1.25, we have log of 2 times 1.25 minus 1, that is approximately 0.18. For x equals 1.5, we will have log of 2 times 1.5 minus 1, that is approximately 0.30. For x equals 1.75, we have log of 2 times 1.75 minus 1, that is approximately 0.40. And for x equals 2, we have log of 2 times 2 minus 1, and that is approximately 0.48. So now that we have the following x and y values, we can now plot these points. Again, for our function log of 2x minus 1, we acquired the following points. 1, 0, 1.25, 0.18, 1.5, 0.30, 1.75, approximately 0.4, and 2, approximately 0.48. So plotting these points, we will have 1, 0, 1.25, 0.176, 1.5, 0.301, 1.75, 0.398, and 2, 0.477. So, connecting these points will give us the graph of our function log of 2x minus 1. Now let's discuss the characteristics, restrictions, and trends in our logarithmic functions. Generally, we have the logarithmic function expressed as f of x equals a times log of x minus c with the base b plus d. Now, how are these values can affect our graph? So, we have first restriction, b should be greater than 0, or b is greater than 0. That can be b is greater than 1, or b is between 0 and 1. Also, b should not be equal to 1. We will discuss later on why these restrictions are necessary. Next, for our horizontal shift, that is dictated by the value of c. So, what will happen if c is positive and if c is negative? For our vertical shift, that is dictated by the value of d. So, what will happen if d is positive? And what will happen if d is negative? And lastly, the stretch of our function is dictated by the value of a. So what will happen if a is positive and if a is increasing? And what if a is negative? Now let's discuss why b should be positive. In our first example, we have here y equals log of x to the base 0. In this example, our base is 0. Transforming this into exponential form, so from log of x to the base a equals b, it will become a raised to b equals x. So from log of x to the base 0 equals y, it will become 0 raised to y equals x. But we know that 0 raised to any number is undefined at certain values. Next, what if our base is a negative value? In this case, y equals log of x to the base negative 2. So transforming this into exponential form, again from log of x to the base a equals b, it will become a raised to b equals x. So from log of x to the base negative 2 equals y, it will become negative 2 raised to y equals x. Graphing an exponential function with negative base is not consistently increasing or decreasing. Now let's discuss why b cannot be equal to 1. So for this example, we have here y equals log of x to the base 1. Expressing this logarithmic function into exponential form, so from log of x to the base a equals b, it will become a raised to b equals x. So the given log of x to the base 1 equals y, it will become 1 raised to y equals x. We know that when we raise 1 to any number, the answer will always be 1. Graphing this will only produce a straight line. Now let's see what will happen when b is greater than 1 and b is between 0 and positive 1. We already established that b should be a positive number or greater than 0 for our function to produce real values. But specifically, what will happen to our graph when our value of base is greater than 1 or between 0 and positive 1? In our first example, we have here f of x equals log of 3x to the base 2. Our value of b here is positive 2, which is greater than 1. So we can see that this function produces this graph. Now let's see the value of x and y. As x is increasing, so from 0 to positive infinity, we can also see that y is also increasing, so from negative infinity to positive infinity. Now let's look at what if our value of b is between 0 and positive 1. So in this example, we have here f of x equals log of 3x to the base 0.5, and that is b is between 0 and positive 1. We can see that as x is increasing, direction of our y value or the graph is decreasing. So that is the main difference between the values of b. Now let's see what happens when c is greater than 0 and c is less than 0. We already know that the value of c dictates the horizontal shift of our function. So now let's see what is its effect to our graph. So our first example is the function log of x. And by typing it to our graphing calculator, it produces this graph. For our function log of x, our value of c is equal to 0. Now let's look if f of x is equal to log of x minus 4. In this case, c is equal to 4 or c is greater than 0. We can see that from our original function log of x by adding minus 4 or by letting c equals 4, our function shifts from this point to this point. Or basically, it shifts to the right. Now let's see if f of x is equal to log of x minus negative 4. In this example, we have c equals -4 or c is less than 0. We can see that from our original function, which is this graph or this curve, it shifted to the left. So it became this graph. So in short, if c is less than 0, our graph will shift to the left, and if c is greater than 0, our graph will shift to the right. Now let's see what will happen when d is greater than 0 or when d is less than 0. We already know that d dictates our vertical shift. So let's look at them. So this will be our reference function. The function f of x equals log of x to the base 3. In this example, d is equal to 0. Now let's proceed to our next function, where f of x is equal to log of x to the base 3 plus 5. In this example, d is equal to 5, or we let d equal to 5, and that is d is greater than 0. It is obvious that from our original point, or original graph, our graph shifted upwards. Next, we have f of x equals log of x to the base 3 minus 5, and we let d equals -5. Or this is our example for d less than 0. In our graph, we can see that from the green graph or the green curve, our graph shifted downwards. So to summarize, when d is greater than 0, our graph will shift upwards, and for d less than 0, our graph will shift downwards. Now let's see what will happen when a is greater than 0 and when a is less than 0. We already know that our value of a determines the stretch of our function. So in this example, we have here f of x equals 3 log of 2x. Next, we have here f of x equals 5 log of 2x, and we have here f of x equals 7 log of 2x. Our 3 log of 2x is represented by the green curve, 5 log of 2x is represented by the violet curve, and lastly, 7 log of 2x is represented by the black curve. So we can observe these are the values of a. We have 3, 5, and 7. We can see that as our value of a increases, so from 3 to 5 to 7, our graph stretches upward. So from green to violet and to black. So same with negative. So what we did here is we let a be negative number. So from 3 log of 2x, it became -3 log of 2x. From 5 log of 2x, we make it -5 log of 2x. And from 7 log of 2x, we make it -7 log of 2x. So same with negative, we can see that the numerical value is still increasing, thus the stretch also increases. However, since the sign is negative, we can observe that the graph also decreases. Now let's discuss the zeros, intercepts, and asymptote of logarithmic function. So in this example, we have f of x equals log of 2x plus 0.25 to the base 4. And that is represented by our red curve. The graph of our function passes through the x-axis and the y-axis. Where the graph passes through the x-axis, that is our x-intercept. And where the graph passes through the y-axis, that is our y-intercept. Our x-intercept in this case is 0.375, 0, and our y-intercept here is 0, negative 1. And by taking the x value of our x-intercept, that is the zeros of the function. Now, we take the argument of our function, and that is the 2x plus 0.25. When we equate 2x plus 0.25 to 0, that is this point or this function, it is represented by this violet line. Again, when we equated our argument to 0, that is this line. And this line represents the asymptote of our function. And for our last example, we have here f of x equals log of x plus 9 to the base 3. This function is represented by this red curve. This function is represented by this red curve. Again, this function or this curve passes through the x-axis and the y-axis. Where the graph passes through the x-axis, that is our x-intercept, and where the graph passes through the y-axis, that is our y-intercept. In this case, our x-intercept is negative 8, 0, and our y-intercept is 0, 2. Again, if we take the x value of our x-intercept, so in this case, that is negative 8, that is the 0 of our function. Next, if we take the argument of our function, in this case, that is x plus 9, and equated it to 0, so we have x plus 9 equal to 0, this equation is represented by this line. And this line is our asymptote. And that's the end of our lecture. What we learned how to graph a logarithmic function, supplied missing values in table of values of logarithmic function, determined the parts, trends, restrictions, and characteristics of a logarithmic function. In our next video, we will learn the domain, range, intercepts, zeros, and asymptote of logarithmic functions. For supplementary problems, you may refer to QuexBook General Mathematics Chapter 3.